Hi, thank you for watching. I'm Michael and I'm about to present to you our student Songpeng's work on modeling fixations with neural attention. When we read text, our eyes jump from word to word, or indeed from character to character, and we jump over many and fixate a few. This process has been of interest to psycholinguistics for a long time, and there are some well-established sophisticated models like Easy Reader, Swift, and others that have a sophisticated analysis of the saccade generation and word recognition process. In this project, our aim was to see whether we could replicate some of the success of these kinds of models using a simple rational modeling approach that further is built on modern neural network models as we have in NLP. And so one key motivation for this question is that such rational models can naturally account for task variability, because in task variability and flexibility, humans adapt their behavior in such a way that they can read efficiently. So we wanted to start by asking whether we can account for properties of ordinary reading for a simple reading task using a rational modeling approach where we model reading as optimizing a trade-off between reading well and recognizing the words correctly, but also reading efficiently and fast. We propose a neural network architecture that has a bunch of components. So there's the input words S1 through S3, and there's the key is an attention controller network that decides how far to jump, which characters to jump over in the next saccade. And here, note, we only model forward saccades. We assume that the the model always jumps forward. We don't have regressions built in at this point. So the attention control decides what part to fixate next, and this is then input into a reader module that receives the parts that have been read and memorizes those. And at the end, the model is asked to repeat the input, and this task forces it to recognize the word successfully. So at the end, it can actually repeat the input, including those parts that weren't directly fixated, but were only seen either in the paraphobia or can be recovered from the parts that were seen. The model is trained for a rational objective function that trades off the difficulty of reconstructing the full input. So the model is incentivized to read well and recognize the words correctly, while minimizing the fixation rate, asking the model to read efficiently and fast. The two are traded off by parameter alpha that can be adjusted to, in some sense, change the trade-off of reading well and reading fast. The model is optimized using reinforcement learning, using policy gradient, and it's trained on a large corpus of new text. There is no eye tracking data directly used to train the model. So we do fit two free parameters, the alpha and the window size for the parafobial preview, to match the human fixation rate. But with the exception of that, everything else is unsupervised. And in this sense, the model is quite different from previous models of saccade generation, because it's built on this objective function, and we don't put in and in this sense, the model it appears quite different from previous models like Easy Reader and Swift and others that do not build on this kind of rational objective function, that are instead based on some kind of more sophisticated analysis of the saccade generation and recognition process. So we asked how well this kind of model can do in predicting properties of human fixations. So we evaluated on the Dundee corpus, the corpus of English native speakers reading news text. And what you see here is first the accuracy of fixation location prediction, which we evaluate using a simple Euclidean distance metric to the next human fixation point. Our model is in green. You see it has a relatively low Euclidean distance compared to a random baseline, and also to the established and very sophisticated, certainly, Easy Reader model, suggesting that our model does capture something relevant to human fixations, even though it's unsupervised. There's no human gaze data that entered the model. Here you see fixation rates by word length. In blue, you see for the humans, longer words are more likely to be fixated, which makes sense. Our model in green has a higher fixation rate, but you see a very similar qualitative behavior. To a lesser extent, you see the same thing also for easy reader in red. You see there's also effect by word frequencies. More frequent words are less likely to be fixated in the humans in blue, and also for our model in green. And you see the same thing for easy reader in red. There are similar patterns for fixation for parts of speech going beyond frequency and length, in fact. And you see there's probably similar patterns for the humans in blue as for our model in green. So you see that the fixation rates for our model are consistently higher than the humans, and that's in fact because we matched, here we are showing results where we matched the model's fixation rate to that of easy reader, which exhibited a higher fixation rate than the humans did. Here I'm showing you the landing position in words of different lengths. You see our model again in green with broadly similar patterns to the humans in blue and also to the established easy reader model in red. To conclude, I presented to you a simple rational model of fixations that is based on modern neural network models, as we have NLP and reinforcement learning. It is trained to trade off successful recognition of the words with minimizing the fixations. And with this kind of simple architecture replicates aspects of human fixation behavior both qualitatively and quantitatively in the Dundee corpus, and compares well and favorably with specific well-established models of cat generation and the easy reader model, suggesting that this kind of simple rational approach with neural network models and reinforcement learning is a promising approach to capturing aspects of human reading behavior. In the future, we'll be very interested in also extending this more to task variability and accounting for how humans are flexible in how they respond to different task demands in their fixation behavior. Thank you.